Okay, let's we will start with the law of cosine first, law of sines, extended law of sines. This is, let me write also the name for the picture, for the sections. So it is in the book, it is 1.1. That is the extended law of sines. So we will prove this. Remember, what's the law of sines? Remember, also, we don't know the proof of this. Probably you don't know that if you take any triangle, ABC, with sides A, B, and C, then A over sine A is equal to B over sine B, and that's equal to C over sine C. So this is little c, this little c, this capital C. This extended, it will be a little bit extension of this this theorem. That is, let me write as a theorem, the extended law of sines. Okay, that it says, so let ABC, let's do it like this, be a triangle. And let, and let, let's say C be the circle passing through, the unique circle passing through ABC. Namely, it's a circumcircle. Circle of this triangle ABC. So let O be the center of this circle C, and O be the circle, and let, and R be its radius. I will draw a picture in a moment. So let me draw a picture like this. So let me first draw the circle and the rectangle, triangle. So first we have triangle, and then we draw this circle, circumcircle. That's the center here. That's the center. And this is the radius, R. Okay. Now the extended law of sines says then this A over sine A is equal to B over sine B, and that's also C over sine C, and that's equal to 2R. So A is, of course, this side, B is that side of the triangle, and C is that side. And of course, I draw a acute angle triangle, but it may not be acute. So here's the proof of this statement. So there are two cases. Let me draw this circle once again. So it may be an acute angle triangle like this, or one of the angles might be like that, or maybe let me draw as in my notes so that I don't confuse in the lecture. It's something like this. Let me draw. Oops. Yes, I should be a little bit more careful. I can use some ruler. Okay, that is ABC, A, B, C, or it may be like this. Now, let's look at the, so the center now is outside of the triangle. Now, we use a different color. Now let's draw this line, the diameter is passed from C. Oops, that's not good. It's not good. Okay, something like this. And here also, something like that. It's supposed to pass through this O origin. Now, when you look at this, the angle at B, when you also connect this point J, let's connect this point J to B, like this. Then this angle is a right triangle. This angle is right because, yeah, because this is diameter, and that angle is right, which means this angle is right. And let, okay, next. Now let alpha denotes, I guess 90 minus A. Usually. Now, why did I say that? I guess this is not necessary. In case, I will let you know. This may be incorrect. So now the angle, as we said, the angle at B in these both pictures are 90 degrees, so that the angle at J is equal to the angle at A, because they subtend the same arc. So the angle at J and the angle at A subtend the same arc, so that J is equal to A. So this is equal to A. And also here. So, but on this side, they don't subtend the same arc. It is, I suppose, this is alpha. Yeah. Now this is we have a on this picture, in the second picture, we have a quadrilateral, so that if this angle is A, that angle is 180 minus A. Let's call this alpha. So let alpha be 180 minus A. So that sine A in both pictures, sine A is equal to sine J. So sine J in both pictures, they are the same, because sine 180 minus, the reason is that sine 180 minus alpha, my A is sine A, property of function sine. And that's equal to the sine, if you look at this red triangle, including with BC, then it is A over, this side is A, and sine J is, from the first picture, sine J is A over the diameter. The diameter, yes. And therefore, A over sine A is equal to 2R. So this is the first, one of them. And similarly for the others. If you do the same thing for other sides, other vertices, we have B over 2R is equal to B over sine R, sine B is equal to 2R, and C over sine C is equal to 2R. And that's the end of the proof. Okay, this is simple observations using the previous last lecture's results. We use two things. If two angles on the whose vertices are on the circle subtend the same arc, then they are the same. And if we have an inscribed quadrilateral, then the sum of the corresponding angles is 180 degrees. There are only two things we used, which we proved them before, so that we have the law of sines. And here's a notation for this lecture. We will always, given triangle ABC, so A will denote the angle. A is the angle. The angle BAC, or its value, yeah, and similarly B, ABC, and A times B is the length of the or the distance between A and B, or the length of the line segment. Between A and B. There's also, well, the area is of this triangle ABC. It is denoted in this lecture ABC, like inside the parentheses, and the area of a quadrilateral. Let me write for short. Quadrilateral, let's say ABCD is will be denoted by ABCD, etc. Okay. But every time I will tell what is ABC as the area, etc. So this is the first. This is the first section. And second section. In the second, do you have any questions? If you have any questions, just stop and ask me. Okay. Next, the Sevas theorem. This is 1.2. Let me write 1.2. I pronounce it as Seva, but this guy is Italian. He lived something like 1670s. Around that time, he proved this theorem. I looked at Google Amja, and it says something like Chiva or Cheva, but let's call it Seva for short. I mean, Okay, here's a definition. So, definition. So, given, let me write with a picture, the line segment. So let's draw a triangle like this. So by the way, this will be always A, B, C. Well, it will be always in this order. And if you join one of the vertices to the other side, the corresponding side, that's called a serium. So that's the more precisely the line segment. The line segment joining a vertex, of a triangle to any point of the opposite side is called a serium. And one more definition. This is which we will use this terminology for a set of lines are called concurrent if all of them pass through a point something happened. See, erase. Okay. What happened? If they all pass through, if all of them pass through a point P. Now, namely, this, what is this? Cancel. Okay, namely, so we have a line, we have another line, we have, forget about this, others, something like this. So that's the point P. So these lines are concurrent. Of course, if two lines have two distinct points in common, then they are the same line. Okay, here's a nice theorem of Seva. This is from 1678. This is a very old theorem. So geometry is a beautiful subject, and it has been studied for a long time, since ancient times. So there are many interesting things that we do not teach in lectures, I mean, we don't see in the lecture, so that, but this, it seems nice, and this book gives such an introduction to, I mean, such properties of these theorems. So here is one such example. So let A, B, C a triangle. And let AX, BY, CZ be serials. Namely, let's draw a picture here. So we have a triangle like this, and we have serials. Let me draw it like this. So this is the point X, that's the point Y, that's the point Z. Go like this. And the statement says if AX, BY, CZ. Now, of course, here we mean these lines, not their lengths, are concurrent. Then the Bx over xc. Now we mean the length of this. Bx means the length of the distance between B and X times, so this side over that side, and then Cy over Ya times Cy over this side and over that side, and similarly Az over Zb, that is always 1 if they are concurrent. Did you know this before? Did anybody know this theorem? Have you seen this before? I didn't know. But it has a nice proof. Okay. Now, let's look at the area of ABX, triangle ABX. What is ABX? Here. Look at this triangle ABX, A, B, and X. Let's say this is, we have some H. Any problem? No. And this is Bx times some H over 2, right? H is this height. H is that height. That height. And AXC, if you look at the other triangle, the height is the same, so that it is XC times H over 2. Its area. And also, if you look at, what's this? P. This point is P. If you look at PBX, this triangle, it is Bx times some H prime over 2. H prime is this height from the distance between P and the line segment Bx. that height. And PXC, if you look at the other triangle, the height is the same. With this, these two triangles have the same height. It is XC times H prime over 2. So therefore, if you look at BX over XC, it is BX over XC. If we divide this side by side, then H's will disappear. So we will have A BX, the area of A BX over AXC. And that is also from the right hand side, this is also equal to PBX over PXC. This area, PBX, this area over that area. So that now this is also equal to ABX over minus PBX over AXC minus PXC, and that is, if you look at ABX minus PBX, that is ABP. What is ABP? So it's we have. I will explain this in a moment. The first equality. So this equality comes from this fact that if you have A over B is equal to C over D, then you can check that. Let's say suppose C is less than A, you can check that that's also equal to A minus C over B minus D. Yeah. Okay. That's the inequality, and this equality is this equality is that the area of ABX minus the area of PBX is the area of ABP. So this area, this white, the area of that triangle. And in the denominator, we will have AXC minus PXC is CAP. So AXC is this big triangle minus this shaded area is the area of CAP. This area. Okay, now we did this for the one quotient, and if you do this for the others, let's look at this triangle again. So BX over XC is this area of this triangle over the area of that triangle. Okay, now if we do this for the other sides, so this is BX over XC. So let's put it like this. And similarly, BX CY over YA will be the area of CY over YA. It will be the area of BPC over ABP. BCP over ABP. Let me draw once again like this. So this is this CY over YP, BCP, this shaded area over this shaded area. Okay, and AZ over ZB. Similarly, I can use different color, right? Let me use the different colors for shading. Oh yeah, this one. But this is AZ or ZB. It will be the area of this triangle, this part, over the area of that part, area of this part, which is the CA. This is CAP over the area of BCP. So therefore, we have 2, that's 3. So if you look at BX over XC times CY over YA times AZ over ZB. So these letters are the same. So the next, these are the same, etc. This is, let's write everything together. A, B, P over area of CAP times area of BCP over ABP times the area of CAP over area of BCP. Now, this ABP and ABP will cancel. CAP and CAP will cancel. And the others will cancel as well. And as a result, we will have only 1. So numerator and denominators are the same, so that's equal to 1. That's the proof of Sevas theorem. Isn't that nice? Are you here? Everybody? Okay, it's good. Yeah, I like it. When I first read this, I said, it's cool. I didn't know this before. At the end of the book, at the end of each section, there are exercises. There are exercises at the end of each section, and try to do them. And there's also at the end of the book, there's also hints for these exercises. So you should look at the hints and then solve the problems. Does everybody have a book? Or does anybody have the book?
Yes, I have the book.
Me too.
Me too.
Olmayan? Var mı? I guess not. Okay, just let me know, or just email know if you don't have the book, PDF file. Okay, let's finish this recording now, and because I finished this first. Oh, by the way, I did not finish, but I will also prove the converse of this statement. So the statement says, here it says, if we have 3 seriums, and if they intersect at one point, then this product is 1. But this converse is also true, and I will prove in the at the beginning of the next lectures. Okay, let's give a break, 10-minute break. Let's start at again 40 on time. Let's finish.
Hocam
Just a second. Stop recording. Where is stop recording?